Hi there, this is TK Tinyiko Kosa welcoming you to a beautiful revision in physical sciences, and of course now we're looking at paper 1, and specifically in paper 1 we will be talking about electricity. And in this electricity, of course, let me just show you and unpack it to you as to what is required of you to really make sure of knowing, so that at the end you can tell yourself, I understand all the necessary aspects when it comes to electricity. Now, here you need to know that there is this principle here, the principle of conservation of charge. You should be able to state it, you should be able to apply it. And here we're talking about when things collide, carrying this so much charge, that much charge collide. This system of charge in a closed system can never change. It remains constant. It can't be more, it can't be less. All right. So the next thing that I want to make you aware of is the following. All right. Let's have a look at this. The next one. State and apply Coulomb's law. You need to know this one. And here again, we're talking about isolated charged objects. Okay. Here it's Coulomb's law. Forces between charges, because they are carrying forces between two objects that are carrying charge. You need to be able to use that law there. You need to be able to sketch the electric field formed around charged objects. Whether we're talking about uniform electric field, as we're going to show in the revision session, or we're talking about non-uniform, you should be able to sketch those type of electric fields. You need to be able to calculate the electric field strength and the electric potential at a point. Okay, okay. Now, the electric field potential, all right, there you know the equation that you have to use and where it comes from. We should be able to revise and get to that point. Next, you need to be able to define and calculate the potential difference between 2 points in an electric field. You also need to be able to define, calculate the capacitance of a capacitor. So we're going to talk about those things as well. You also need to be able to describe changes in electric current and the potential difference in a circuit in which a capacitor is used, either when it is charging and when it is discharging. You should be able to understand changes in the current and the potential difference there. You need to be able to state and apply Ohm's law to electric circuits, all right? And also to define and apply the concept of EMF when it comes to electric circuits. So those are the basic things that you need to know when we talk electricity. Okay, now let's move on with our revision. I am now coming to a question here that will introduce you to this revision session that we're having here. We're calling it question 1, but it is from the November 2012, okay, end of year question. It was question 8 then. In a circuit represented below, an uncharged capacitor, so the capacitor is not charged, is connected in series with a 1000 ohm resistor. The EMF of the battery is 12 volts. Ignore internal resistance. So now this is a keyword. You need to ignore the internal resistance of the battery and that of the ammeter. Okay? And that is your circuit there. All right? There is the circuit. Calculate the initial current in the circuit when switch S is closed. So when this switch is closed, what will be the current in there? Now look, this is direct from Ohm's law. You've got I current equals V over R. Okay? And what will that be? So that will be your V is 12 and your R, that is the resistance that you're having, total resistance in that circuit. So that will be equal to, you work it out with your calculator quickly, so you've got 12 divided by 1000. And what do you get? You've got 0.012. And because we we're working into, into 2 decimal places after a comma, you can call this 0,01 because it was 0,012. And what is this that you have calculated for? This is current. It is measured in amperes, so you need to put A there for the unit. Okay. The next question on it says, write down the potential difference across the plates of the capacitor when it is fully charged. Now, listen to this question here. It says write down. You don't have to calculate. Now, when it is fully charged, it means the whole potential difference that is given to you there, the EMF, is what is across the terminals of that capacitor. So that will be 12 volts. Okay. Now, moving on with the question. Coming to C. C says calculate the charge stored on the plates of the capacitor when it is fully charged. Now, for us to calculate for this charge stored there, we need to know the capacitance of this capacitor. And we are told here that the capacitor has a capacitance of 120 microfarad. Okay? So for us, we can then use this equation here that says capacitance is equal to charge over the potential difference. And from there, what you are given is the capacitance here, C, which is 120 microfarad. So that will be what? That will be 120. Because we don't work in microfarads, we need to convert that. This will be by 10 to the power minus 6. That will be equal to, charge is what we're looking for. The potential difference V is 12 there. Therefore, our Q charge is 12 times, I'm doing this for the sake of those that really battle to work out things. So 120 by 10 to the power minus 6. Then you work that out with your calculator. Right now, taking out the calculator so that we can work this out, we've got 12 times 120 by 10 to the power minus 6. And let's see what we have there. What we have is 1.44 by 10 to the power minus 3. So the answer here is equal to 1.44 by 10 to the power minus 3. What are we calculating for? Is charge. So this is what? Coulombs. Okay? Just to make sure that the answer we got exactly as is. Okay? Now, that's what we have. And moving on here, let's have a look at this last part here of the question. It says, after discharging the capacitor, it is connected in the same circuit to a resistor of a higher resistance. Now the resistance is now higher. It's no more 1,000 ohms. And switch as is now closed again. How would this change affect each of the following? Write down increases, decreases, or remains the same. Now, the first one that we need to talk about is the initial charging current, like we calculated earlier on. Will it remain the same? Will it be greater? Will it be less? The answer here is that it is going to be less. So the charging current is going to decrease. So the answer here that you're going to go for is decreases, because that's what you have been asked to choose from. Okay? And if the current has decreases, the charging current has decreased. Now, look at the next part of the question. It says, what will happen? Say again whether it's going to decrease, increase, or remain the same. The time it takes for the capacitor to become fully charged. If the charging current has decreased, the charging time is going to increase. So the answer for this one will be increases. Okay, so that's what we had for that one there. Now, Next, on the same question, it says the two parallel plates of the fully charged capacitor are 12 millimeters apart. Sketch the electric field pattern between the parallel plates. Now, you would see here, I have here something that says uniform field pattern. If I've got a capacitor, the plates are parallel, and what I will have here is a uniform electric field. Okay? So, uniform electric field, what you need to make sure about, so let me just draw it in here. So let's say this is my, let me see if I can have some lines here. Okay, so that's my first charge there, and then the second plate down here. Okay, so those plates are parallel to each other, and this one is positive and this one is negative. What I would have here are electric field lines that are parallel to each other. I'm trying to make sure that they are equidistant from each other, okay, so that you see how to do this. All right. Okay, now I may not have had, now at the end here I would have the ones that are bulging out like that. Okay, now I need to explain here. This is a uniform electric field, okay? Uniform electric field. This distance here has to be the same to show that we have got a uniform electric field. Okay, now the other thing that you needed to do, so that in an exam is going to get you a mark. The next thing that I need to make sure is that if this is my positive and this is my negative, the direction of the field, is from positive to negative. Okay, so you can see my arrows there. I need to have that. Right, so that's what I have. And I also need to show that at the end where the parallel lines end, these are your plates of your capacitor, there shall be some bulging. That bulging there, that has to be shown as well for you to get full marks here. So please make sure that your field lines are equidistant from each other when you've got parallel plates to show that uniform field. Now, if the field was not uniform, say this question here asked you for something that was, say, a field around a positive sphere, all right? So here you would be able to say, okay, what I know would happen here is that I would have fields like that, okay, field lines like that, or the field lines like that. Trying to get this nicely done, okay. Okay, they don't get into the sphere as such, but then they are from the sphere, from the surface of the sphere and radiating outwards. So this is not uniform. This is a non-uniform electric field pattern. Now, look at it. When field lines are closer to each other, field lines closer, okay? When they are closer, field is strong. Okay, so here we're talking about strong field. Okay, so I'll just write strong field there. So in here, the field is strong. But as you move further away from the charge, the field becomes less strong, okay? Further away. The field lines are actually spreading out, getting further and further away from each other. And that indicates that the field is weak. Okay? So the field is weak. The field strength is weak there. Now, this holds for this equation here. I think you'll remember it. That shows that the electric field strength, okay, the electric field strength E is directly proportional to the charge and inversely proportional to the square of the distance, okay, of the square of the distance at that point where we want to find the field strength. Okay, good. Now, moving on, the two parallel plates of the fully charged capacitor are 12 millimeters, as we have said that. Now, calculate the magnitude of the electric field strength at a point midway between the plates. Now, look, the field there is uniform. Okay? So we can't use this equation here. This equation doesn't apply. For uniform field, which is the field between the plates of a capacitor, we would have to use this one, E equals potential difference over D, given what is there for us there. Okay, okay, or you can use E equals F over Q. Okay, but we don't have information to be able to use this one here. Although this one would be applicable, but the information that is given to us in this question doesn't allow us to use that. So what do we need to do here? We just come here and say, okay, we've got EMF is 12. The distance between the plates is 12. So this would 12 millimeters. We don't work in millimeters, we work in meters. So you convert that. Multiplied by 10 to the power, multiplied by 10 to the power minus 3, converting that to meters. Okay. Right, so taking the calculator here so that we can get the answer to this sum here, we have got 12 divided by 12 by 10 to the power minus 3, and the answer is 1,000. So what you have there is 1 by 10 to the power 3 watt. You've got volts divided by distance, so this is volt per meter. Okay, that is the unit of measurement there. Okay, so that's what we had to do so far, and now we're going to have a short commercial break, and when we come back, we're going to continue to talk more about electricity and going further into electric circuits. Welcome back, and as I've promised just before the break that we're going to continue talking about electricity and we're going to bring in some circuit problems. That's exactly what we're going to do now. Let's have a look at this question here. This is question number 2, all right, according to us, adapted from the November 2012 paper 19.1. Okay, it says here, in the circuit represented below, two 60 ohm resistors are connected in parallel, and they are also connected in with another resistor in series. This other resistor is 25 ohms. The battery has an EMF of 12 volts, and the internal resistance of the battery is 1.5 ohms. Okay, now here is the circuit diagram that they are talking about here. There is the parallel connection, there is the series connection. You also have your internal resistance there. Okay, now let's just go through the questions quickly. 1, calculate A, the equivalent resistance of the parallel combination. So we should be able to do that. B, calculate the total current in the circuit. From the given information, we should be able to do that as well. And C, the potential difference across the parallel resistors. We should be able to do that. Okay, then moving on, okay, to actually working on those questions there. Let's look at it. The first one was saying calculate the equivalent resistance of the parallel connection, which is this part here. How do we do that? Remember the formula, 1 over Req, equivalent, would be equal to 1 over resistor 1 plus 1 over resistor 2. Now, 1 over Req, I prefer to always write it down so that it reminds you to invert at the end. This will be 1 over 60 plus 1 over 60. Therefore, your 1 over Req works out to be, your LCM here is 60, so you're going to say 16 to 61, 1 times 1 is 1, plus 16 to 60, 1 times 1 is 1. And therefore, from here, you can be able to say that your equivalent resistance for the parallel connection is 60 over 2. Now you have inverted, and what do you get? I mean, you don't need a calculator for that one. That is 30 ohms. So we have gotten that one there. Right. Next, coming to number B. What does number B want us to do? Number B says calculate the total current in the circuit. Now you would know that I is equal to V over R. But from the information that we have, we cannot just go straight and begin to use that particular formula there, okay? Because what we have is the internal resistance, what we have is the total resistance, and what we have is the EMF. Now, we need to think of another formula that can help us to do that. And quickly, you can see that the one that says EMF is equal to current, total current in the circuit, which is what we're looking for, in brackets, capital letter R for total resistance externally, plus small letter r for the internal resistance. What is EMF? E, it's 12. So 12 is equal to total current into, what is R here? You can quickly get your R basically, because your R total externally should be equal to what? Your equivalent for parallel plus the one in series. So what do you get there? You're getting that as 55 ohms. So you would then put the 55 ohms here plus R, small r for internal resistance. It's given to us as 1,5 ohms. So you put it like that. So you've got 12 equals I times 56,5. When you add these ones together here, they give you that. Okay. Now, I'm doing this for those people who are really, really struggling to do some mathematical operations. So this will be 12 divided by 56,5, and therefore you're getting your current to be what? Take your calculator immediately. You say this is 12 divided by 56,5, and you get your answer to be 0.21 amperes, because that is current there. So your I is 0.21 amperes. Okay, so we've been able to answer number B here that talks about total current in that circuit. The next question on this is saying, is number C here, that says find the potential difference across the parallel resistors. Now, potential difference across the parallel resistors would be given by total current times the resistance, the equivalent resistance around the parallel connection. So that will be equal to what? 0.21. We have just calculated for that, times, what is the RP? Is 30, the equivalent resistance of the parallel section. Again, don't waste your time by trying to find that manually, okay? You just have to use your calculator there. So this is 0.21 times 30, and then what do you get? You're getting it to be 6.3. So this is 6.3 volts. This is the potential difference, so we're talking about volts. Remember, when you're doing any calculations in science, at the end of it all, make sure you put in the relevant unit for what you are calculating for, because this is not mathematics, it's physical sciences. All right, now, moving on. We're coming to question number 3. Question number 3 says here, this is from the November 2012 paper 1 as well, 9.2. It says, learners conduct an investigation to determine the EMF and the internal resistance of a battery, okay? They set up a circuit as shown in the diagram below, but for our diagram is the diagram above there, okay, as you see it, and measure the potential difference using the voltmeter for different currents in the circuit. The results as obtained are shown in the graph below. So they graphed their results like that, okay? So you can see it's a graph of potential difference versus current. Then the questions. All right. Use the graph, says use the graph to determine the EMF of the battery. Now, for them to get the EMF of the battery, as soon as they switch on this circuit, that's what they found out. So what would be the EMF of the circuit? The EMF of the circuit is of the battery is 1,5 volts. Okay. Now calculate the gradient of the graph. Now, if you look at this graph here, the best way we can actually maneuver, we can actually work on it is to say, okay, that is the beginning. So let's take that point and take the end point as well. If we take these 2 points, we should be able to find the gradient. And what will be the gradient here? Look. Gradient is change in the vertical divided by change in the horizontal. Now, what is in the vertical for us? It's V. So change in V over change in I. What is in the horizontal is the current. Okay, now V over I is resistance. You can see that already. Right, so let's put some values here and try to read this graph here. You would see here that at that point, that is 0.1, 0.2, 0.3, 0.4, therefore that is 0.5. So this would mean here is 0.6. Now that will be, this will be 0.7, but this point here is not here. So that will be 0.7 there. All right. Now it's not there. This point here, it's here. It's here. So that would mean this is 0.65. Okay, so we can get that reading there. So if we have that, let's then, this is for potential difference. Let's then look for the current. For current, you having, that is 0.1, and here that is 0. So we can be able to calculate our gradient here. So change in V will be this 0.65 minus 1.5. Okay, so this will be equal to, 0.65 minus 1.5 divided by, you go back to the graph, you will see the second value for current is 1. The first value is 0. So we'll say this will be 1.0 minus 0. So what do we have? You can then take out your calculator and say, okay, 0.65 minus 1.5. Okay. Yeah, of course, you're going to get a negative answer, but the negative doesn't help us here. It doesn't really make any difference. So you've got minus 0.85 divided by 1. So this is minus 0.85 because it's a negative gradient. But what it means there is that your gradient is therefore 0.85. Okay, so 0.85 What does that mean? If you've calculated the gradient to be 0.85 when you've got this here, I want to bring your attention to this, when you've got V divided by I, what is that? And obviously that brings us to the last question here. Which physical quantity is represented by the magnitude of the gradient of the graph? V over I is what? That is resistance. Okay, so the quantity that we were looking at here is resistance. Okay, so next, how does the voltmeter reading change? Or how does it change as the ammeter reading increases? Write down increases, decreases, or remains the same. Use the formula EMF equal to IR plus IR to explain your answer. So we're looking at how does the voltmeter reading change as the ammeter reading increases. Okay, now in other words, as the current increases. So as current increases, that's what it means. But all we need to say here, does the reading on the voltmeter increase or decrease or remain the same? That one is going to do what? It decreases. Why? The amount of lost volt increases. The amount of lost volts, if you like, lost volts, IR, increases. So the external potential difference decreases according to this. Let's just use that formula there. You would see that if you've got EMF equals I times R plus I times R, okay, this one here is your external potential difference, which is the reading on V. So this IR is equal to EMF minus IR. Now, as I increases, this lost volts increases. So you are subtracting this much lost volts from that, and therefore this one decreases. Okay, so from that formula there, you show that IR, which is V, the potential difference across the circuit, would be equal to the EMF minus IR, and that confirms the fact that it decreases. Okay, now moving quickly, we have got one more question to do here. I hope time will allow us to do so. Let's read it through as well. The circuit represented below is used to investigate the relationship between current passing through and the potential difference across resistor P. All right, so there is the circuit diagram to show what we're talking about there. There is the resistor P. The results obtained are used to draw a graph. Okay, so the graph that has been drawn below is from the results. Let's again try to answer the questions here. Write down the independent variable in this case. When you've got a graph, the independent variable is always the quantity on your horizontal axis. The dependent variable is the quantity on your vertical axis. Now, what is on your horizontal axis here? It is your potential difference. So your independent variable here is what? Potential difference. Potential difference. Okay, now next, write down the variable that must be controlled. Okay, in this case, the variable that must be controlled, it's temperature. Now in science, when we talk about a controlled variable, is the variable that should be made to remain constant. It should not affect the results in that practical investigation or experiment. So the controlled one here will be temperature. These learners that are doing this practical have to make sure that temperature remains constant. See, write down the conclusion that can be made from this. Okay, the conclusion that can be made from this is that the current through the resistor, is directly proportional. It's directly proportional to the potential difference. Okay, so that's what can be concluded here. Okay, and you can see that actually this is around Ohm's law. Okay, now using the gradient of the graph, calculate the resistance of resistor P. Now if we look at the gradient here, let's come back to it. Again, we can just take two easy points. We can take that point and that point, okay, and that point there. Now let's try and read this graph again like we did earlier on. This is 0 from up to there is 0,2, okay? So this should be 0,0, okay, 0,1 should be halfway. 1, 2, 3, 4, 5. That's 0,1. Okay, so this will be 0,2, 0, 0,02, 0,04, 0,06, 0,08, then 0,1. All right, and then from there you are at 2 there. All right, so what will this one be? If this is 0,01, so this is, if this is 0,1, then this is 0,12, 0,14, 0,16, 0,18. So that point there will be 0,18. Okay, just before 2 there. So we have that, we can calculate for the gradient. Now, again, the gradient M, as we know it in maths, the gradient M, in this case, is change in vertical over change in horizontal. In our case, what is on the vertical is current, and what is on the horizontal is potential difference. So it will be change in I over change in V. So that will be equal to, in terms of I, we're taking it from 0,18 minus 0, minus 0, because we're looking at these 2 points here. All right, so it's 0,18, 0,18 minus 0 divided by this one here, 0,5 minus 0,5 minus 0 as well. Okay, so we'll say 0,5 minus 0. Now let's use the calculator. Okay, so here we've got 0,18 divided by 0,5. What do we get as the answer? We're getting 0,36. So we're getting the answer as 0,36. So 0,36. Okay, so 0,36 as the gradient. What we are doing is to use this gradient to find the resistance there of what? Of P. So if we have a situation like this, and I need to emphasize this, where you've got current on the vertical axis and potential difference on the horizontal axis, what you're going to do to find your resultant, I mean your resistance, you're going to invert that, because this is 1 over R. So your R will be 1 over 0,36. Okay, and that will be, so we're going to have that as 1 divided by 0,36, and we get the answer to be 2.78. So this will be 2.78 ohms. So that's it about circuit. We have now completed everything we needed to do about it. We are now switching to something else completely different, and this time we're going to talk about static electricity. Still electricity, but we're talking about static electricity, okay? And therefore, if you remember well, once we talk static electricity, we should be thinking Coulomb, okay? And here I've got a question here. It's question number 5 here. It is from the Eastern Cape Department of Education. It was their September paper, and it was question number 9. Let's just have a look at it. It says 3-point charges Q1 with that amount of charge, Q2 with that amount of charge, and Q with an unknown magnitude of charge. They are arranged as follows. So this is the arrangement, okay? So you've got Q1 there, Q2 there, and Q with no number is in between Q1 and Q2. And of course, the magnitude of Q there is not known. We don't know how big, what the size is for that charge Q in between. We don't know it, okay? Then the first charge, the first question here is, draw the electric field pattern between Q1 and Q2 if Q is removed from the system. Now, you need to go back to this diagram here and recognize the fact that Q1 is positive and Q2 is negative. Now, if I need to draw an electric field pattern between the two, positive and a negative charge, I need to know what is going to happen. Obviously, positive and negative will talk about attraction. Unlike charges attract each other. So my field pattern must show that there is attraction between the two charges. And how does that happen? And of course, if you look at this one here, before I even start drawing it, you will remember earlier on when we looked at the parallel plates from a capacitor and we had to draw the field between them. That time, we were talking about uniform field. So the field strength is the same throughout in between the parallel plates. But in this case, when we're talking about point charges, we're talking about non-uniform field. Okay, so I should note that here I've got a non-uniform field. Okay, so the field is not uniform. It's a field between 2 point charges. One is, let me just try and draw this nicely so that I don't have, there we go. And say this is the positive. Okay, and then I have another one there, and that is the negative. That's Q2, negative, right? So this is negative. All right, so I need to draw the field lines here. First of all, field lines start on the surface and end on the surface perpendicularly, okay? I'm trying to show that. So at right angle onto the surface. Then if it starts perpendicularly there, it will go and come and also land perpendicularly. All right? Direction is from positive to negative. So I would have it like that. Okay? Can have another one like that. Starting perpendicularly, landing perpendicularly. Okay? Like that. And then you can have this. Can have that. Okay? Remember, from positive, radiating out into negative, coming in. So that is the direction of your field. So this would be the drawing that shows the electric field pattern between a positively charged sphere and a negatively charged sphere. And I'm asking you, in fact, requesting you to make sure that when you draw these lines, try and make sure that they look to be landing perpendicularly and radiating perpendicularly from where they come from. Because if you just do them for the sake of doing them, things like this, that is not going to give you marks. That shows you don't know what you're doing. Field lines also do not cross each other. So you can't have a line that goes like that. So that cross cannot happen. So that will be a very horrible, incorrect way of doing it. You don't do that. You follow the way the pattern should be like. And thus will be the way the charges or the electric field pattern is like. Now, I also said to you that here we're talking about a non-uniform field. The field strength at this point, for example, at this point there, it's not the same field strength at that point. Okay, it's different. So E2 is not the same as E1. Why? Because the field is non-uniform. Closer to the charge there, the field is strong. So we've got a strong field. But further away from the field, from the charge, say at this point here, the field is weaker. Okay. So here we have, of course, what we call non-uniform field. Okay. So that's what we have. Right. Let's move on to question number B. All right. Question B says, if the net electrostatic force on Q is 12 by 10 to the power minus 4 newtons to the right, calculate the magnitude of Q. So we need to find the size of Q, charge Q. Now, there's a lot we need to deduce first before we can answer this question here from the given information and from the diagram itself. Let's start with the diagram. Q is in between Q1 and Q2. Okay? There is Q. We are told from the information that the resultant force on Q is 12 by 10 to the power minus 4 newtons to the right. So it is moving in that direction, to the right. Okay? To the right. So there we go, to the right. Now, if it is moving to the right, there is something we need to deduce here. If it is moving to the right, yet Q2 is negative, it means Q2 is attracting Q1, so we assume that Q1 must be positive. So from here, if plus 5 newtons, I mean, this is plus 5 nanocoulombs here, its effect on Q is such that it is pushing Q to the right. It means that it confirms the fact that Q is positive. So there is a force of repulsion here. There is a force of repulsion here, and there is a force of attraction there. Okay, so that's what we have. But then let's just work out the magnitude now. Because the effect on Q is from that force and that force, it means, I mean, from those two charges, it means that we can come up with two equations that will help us solve this problem here. The first equation will be the equation that talks about the force here. So let's call this F1. So for F1, that will be equal to K, Q1, and Q, that one, divided by R squared. Okay? And that will be equal to, This is 9 by 10 to the power 9, that is K, times, what is Q1? It's 5. So 5 by 10 to the power minus 9, because it's nanocoulombs, times Q, divided by, what is the distance between them there? It's 80 centimeters, and 80 centimeters in meters, you divide that by 100, you get that to be 0.8, okay? And then you square that. This becomes our first equation, if you like, so we can work it out. Let's just work it out and simplify it quickly. Okay, so there we go. We've got 9 by 10 to the 9 times 5 by 10 to the power minus 9 divided by, okay, let me just wait there. Okay, by 10 to the power minus 9, then we work that out. You divide that by, divided by 0.8 squared. And what do we get? We're getting that to be 70.31. So this is 70.31. 70.31 Q. This is F1. Okay? So that's F1. Now, F2 is the force here between Q2 and Q. It's this one here. All right? That will be F2. So that one, in the same way, it will be K, Q2 if you like, Q over R squared. That will be 9 by 10 to the 9 times Q2 is what? Q2 is 3 by 10 to the power minus 9. Okay, I'm not mindful of the signs now. I already know the direction in which the resultant force there is. Okay, divided by, what is the distance between them? It's 20. So this will be 0.2 meters squared. Okay, so this will be equal to, you again now bring in the calculator. Let's see if we can simplify that quickly. So we've got 9 to the 9 by 3 to the minus 9. Okay, you divide that by 0.2 squared, and you're getting 675. So that is 675. 675 Q. All right. Now, this is your equation 2, and this is F2. This one is your equation 1, and this is F1. Now, F1 plus F2, let me draw a line there, is equal to, this is the resultant now, is equal to 12 by 10 to the power minus 4. So that's equal to 12 by 10 to the power minus 4. But what is F1? F1 is 70.31 Q plus F2 is 675 Q equal to 12 by 10 to the power minus 4. All right, then you can work this out. So here it means you've got 70.31 Q plus 675. What do you have? You've got 745.31 Q. All right, so 745.31 Q equals 12 by 10 to the power minus 4. Therefore, Q equals that Q equals, okay, let me put it this side. Q equals 12 by 10 to the power minus 4 divided by, what's the other value? 745.31. Okay, so it's 745.31. 745.31. I need to get my point here. 0.31. Okay, and what do we have? That is 1,61 by 10 to the power minus 6. So 1,61 by 10 to the power minus 6 coulombs. So that unfortunately brings us to the end of this revision session. I hope you enjoyed it and you learned a lot from it. You are more prepared than before for the exam now, I believe. Thank you so much for watching, and from me, TK Tinyiko Kosa, is a bye-bye. It is fully charged. Now, for us to calculate for this charge stored there, we need to know the capacitance of this capacitor. And we are told here that the capacitor has a capacitance of 120 microfarad. Okay? So for us, we can then use this equation here that says capacitance is equal to charge over the potential difference. And from there, what you are given is the capacitance here, C, which is 120 microfarad. So that will be what? That will be 120. Because we don't work in microfarads, we need to convert that. This will be by 10 to the power minus 6. That will be equal to, charge is what we're looking for. The potential difference V is 12 there. Therefore, our Q charge is 12 times, I'm doing this for the sake of those that really battle to work out things. So 120 by 10 to the power minus 6. Then you work that out with your calculator. Right now, taking out the calculator so that we can work this out, we've got 12 times 120 by 10 to the power minus 6. Hi there, this is TK Tinyiko Kosa welcoming you to a beautiful revision in physical sciences. And of course, now we're looking at paper 1, and specifically in paper 1, we will be talking about electricity. And in this electricity, of course, let me just show you and unpack it to you as to what is required of you to really make sure of knowing, so that at the end you can tell yourself, I understand all the necessary aspects when it comes to electricity. Now, here you need to know that there is this principle here, the principle of conservation of charge. You should be able to state it, you should be able to apply it. And here we're talking about when things collide, carrying this so much charge, that much charge collide. This system of charge in a closed system can never change. It remains constant. It can't be more, it can't be less. All right. So the next thing that I want to make you aware of is the following. All right. Let's have a look at this. The next one. State and apply Coulomb's law. You need to know this one. And here again, we're talking about isolated charged objects. Okay. Here it's Coulomb's law. Forces between charges, because they are carrying forces between two objects that are carrying charge. You need to be able to use that law there. You need to be able to sketch the electric field formed around charged objects. Whether we're talking about uniform electric field, as we're going to show in the revision session, or we're talking about non-uniform, you should be able to sketch those type of electric fields. You need to be able to calculate the electric field strength and the electric potential at a point. Okay, at a point. Okay. Now, the electric field potential. All right. There, you know the equation that you have to use and where it comes from. We should be able to revise and get to that point. Next, you need to be able to define and calculate the potential difference between 2 points in an electric field. You also need to be able to define, calculate the capacitance of a capacitor. So we're going to talk about those things as well. You also need to be able to describe changes in electric current and the potential difference in a circuit in which a capacitor is used, either when it is charging and when it is discharging. You should be able to understand changes in the current and the potential difference there. You need to be able to state and apply Ohm's law. V is 12, and your R, that is the resistance that you're having, total resistance in that circuit. So that will be equal to, you work it out with your calculator quickly, so you've got 12 divided by 1,000. And what do you get? You've got 0,012. And because we're working into 2 decimal places after a comma, you can call this 0,01 because it was 0,012. And what is this that you have calculated for? This is current. It is measured in amperes, so you need to put A there for the unit. Okay. The next question on it says, write down the potential difference across the plates of the capacitor when it is fully charged. Now, listen to this question here. It says write down. You don't have to calculate. Now, when it is fully charged, it means the whole potential difference that is given to you there, the EMF, is what is across the terminals of that capacitor. So that will be 12 volts. Okay. Now, moving on with the question. Coming to C. C says calculate the charge stored on the plates of the capacitor when to electric circuits, all right? And also to define and apply the concept of EMF when it comes to electric circuits. So those are the basic things that you need to know when we talk electricity. Okay, now let's move on with our revision. I am now coming to a question here that will introduce you to this revision session that we're having here. We're calling it question 1, but it is from the November 2012, okay, end of year question. It was question 8 then. In a circuit represented below, an uncharged capacitor, so the capacitor is not charged, is connected in series with a 1,000 ohm resistor. The EMF of the battery is 12 volts. Ignore internal resistance. So now this is a keyword. You need to ignore the internal resistance of the battery and that of the ammeter. Okay? And that is your circuit there. All right? There is the circuit. Calculate the initial current in the circuit when switch S is closed. So when this switch is closed, what will be the current in there? Now look, this is direct from Ohm's law. You've got I current equals V over R. Okay? And what will that be? So that will be your